can also do Navier-Stokes by finite difference scheme. So this again, I'm going to just sketch it and no code. So we make a 3D grid like that, and at each point, I'm going to compute U. Okay. So this is called pressure correction scheme. I'm just giving you one scheme, which is called pressure correction scheme. Okay, so there are many schemes, but I just sketch one of them. So we write this du by dt like that, u star minus un by delta t. Right hand side, u dot grad is here. Right now, don't think of grad p. Just look at new grad square u. Okay, so you compute this by, let's say, center reference scheme. Okay? Like this. After that, we want to compute pressure in the following manner. Okay. So let's compute pressure like this. Laplacian Pn plus 1 at next time step. Please remember, I'm computing pressure at the next time step. Is rho by delta t divergence u star. Okay. I just compute that. Okay. So this u star is available. I just compute the divergence of u star, which is non-zero because I am not putting grad p. Divergence u normally would expect to be 0, but u star is not velocity right now. U star is not the final velocity at n plus 1. So I compute del dot u star and multiply by rho delta t and solve this equation. This is a Poisson equation. In electrodynamics, remember Laplacian phi equal to charge density minus 4 pi rho. Okay, so this is a source term and this is unknown. Okay, so P is unknown and the source term. There is a ways to solve Poisson equation, which I will do it a bit later. So once we solve it, we get pressure. Okay, once we have the pressure, we can now get un plus 1. So un plus 1 minus u star equal to delta t by rho grad Pn plus 1. Okay, now it's a magic in some sense. Okay, so if I take a divergence of this equation, you see divergence of un plus 1 equal to divergence of u star minus delta t by rho Laplacian p n plus 1. Now, what is this right hand side? From this equation, divergence of u star equal to delta t by rho Laplacian. So this equation is guaranteeing that right hand side is 0. Okay, so we do in 2 steps. We compute intermediate velocity field u star. Using that, you compute pressure and use that pressure to compute the next un plus 1. Okay, so this is called pressure correction. It is very popular scheme. It works. Okay, and you get the solution. Okay, so I will not say much about Navier-Stokes. I'm just telling you the scheme. If you're interested, you can solve for 2D at least. And I made a mistake. Okay, now let's solve Schrödinger equation using finite difference scheme. So this is non-dimensionalized Schrödinger equation. I partial psi t si. Okay, and h is the Hamiltonian operator. Okay. Now I'm going to use leapfrog. Okay, but leapfrog in a slightly subtle way. So we write psi as real part plus I imaginary part, and substitute this here. So you get 2 equations, right? We take the real part and imaginary part of this equation, the real and imaginary part of the equation, and then we get this equation. Partial TR is this times I. So R is only function of I, and partial TI is the R. Okay, so we get d by dt of R is function of I, and di of t by I, well, partial t partial of I is function of R. Okay, so it is somewhat reminiscent of x dot is p and p dot is minus x. So velocity derivative is function of pressure and momentum, and momentum is function of x. Okay. So for this we use leapfrog. Of course, we want mod psi square dx to be 1, conserved. So leapfrog is good for this, and so the idea is that Rn plus 1. Okay, so I think I have in the next slide. So we go from so we have real and imaginary part of psi. So R is going from n minus 1 to n plus 1 using I in the intermediate point. Okay, and I n minus 1 to n plus half, sorry, n minus half to n plus half using Rn. Okay, so this is the slide. So we get, you can see that this is important. So I go from R, let's say R n minus 1 to Rn using I at n minus half. So I at n minus half. So the imaginary part is computed at half integral delta t, and the real part is computed at integral delta t. 1 delta t, 2 delta t, 3 delta t, like that. So here I have I n minus half. So I go from here to here with I imaginary part of the wave function at the intermediate point. Now I go from for the imaginary part, I go from here to here with the real part computed in the intermediate point. Okay, so this is what is written here: Rin minus 1, and we just is the second derivative in x. So we just compute at imaginary part at the midpoint. Okay, it's a midpoint method, or you can call it leapfrog method. Okay, so these are midpoints, imaginary midpoint, and even the imaginary part going from minus half to n minus half to n plus half with r at n. Okay, so midpoint for imaginary part is real part. Okay. Of course, there is a problem at going from 0. So we are given real part and imaginary part at t equals 0. So how do I get half? So first point you can just compute by Euler method for the imaginary part. Okay, and this method is quite accurate. It's nice, and so this is some numerical solution. So we have initial wave function here for the free particle. This free particle, Gaussian wave particle. This is mod psi at a later time, I think t equal to 1. And the real, so mod psi, and so one of them is, so A is the sign is accurate and the dash is numerical. Okay, A is for exact. Okay, so both are lying on top of each other. The imaginary part is this green curve, and the red dash is the real part. Okay, and again the red dash and the blue curve both are numerical and exact value respectively, and both are quite good. I mean, they are close to each other. So the numerical solution is good for Schrödinger equation, and you can adopt this scheme. It works well for time-dependent Schrödinger equation. Is quite good. Okay. Now a linear harmonic oscillator, we can solve it using same method, and I have described it before for spectral method. So the initial condition is half ground state plus half first excited state. Okay, so so we have initial condition like that. This one 0. Then at t equal to 1 we get this, and t equal to 2 we get this, and exact solution is the dashed black curve, which is roughly on top of the numerical solution. Okay, so this also doing quite well. So final difference scheme is not bad as long as we are doing it carefully. Okay, now quickly split operator method. That is quick operator. So split operator method. So we have, remember we have psi t plus delta t is psi t exponential minus IH delta t. Okay. So we can rewrite this as this. So sorry. These are operators. So operator is to the left. So we write this operator into two parts, delta t by 2, delta t by 2, psi delta t. Okay. Now I take this to the left hand side. Okay. So I get e I delta t, psi t delta t is this. Okay. So I have rewritten this here, this one. Now H is a kinetic energy plus potential energy. So we get this Laplacian plus V and this that. Okay. So I just rewrote this H operator as a second derivative half plus B. Okay. So now we can rewrite them in real space. Okay. So real space, it turns out, is pretty, is a tridiagonal matrix. Well, basically the n plus 1 at later time. So you see here we got this t plus delta t is later time, and this is at given time. So we got this is a later time and this is a given time. Okay, so this turns out to be a tridiagonal matrix. So I have not written it here. It's very similar form. This is x, y, y. So you get x, 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 y, y, y. Okay, and psi equal to right hand side. R0, R1, R2, this psi 0, psi 1. Okay, so we get tridiagonal matrix. So split operator will require solution of the tridiagonal matrix. Okay, which we have not done, but this is a scheme I'm giving. Okay, let's quickly compare the two. Okay, so spectral method is more accurate than finite difference scheme. Comparison between more accurate than finite difference scheme. The spectral method requires idealized boundary condition, but finite difference method is for arbitrary boundary condition. We not used it, but it can be done. If you do advanced course, you'll do that. And FD methods are easy to parallelize, which we are not doing it right now. But for big cores, we need to use many computers, and FD method is quite good.